We are continuing through Chapter 2, and the topic today is problems involving temperature changes. Now, some of the things that I would suggest to you are, that we already know, is that due to temperature changes, different types of material expand and contract. If, generally speaking, a material will expand if the temperature is high, and if the temperature is low, that they will contract. One of the examples that I like to point out about that are sidewalks. And if you're looking down on a sidewalk, sidewalks are generally laid out in blocks of concrete. And in between there will be a little joint, which is an expansion joint. And if this joint is not big enough on a hot summer day, the concrete will actually get larger to the point that that expansion joint will disappear. The concrete will push against the other blocks of concrete and it will buckle. So you'll get, if you look out in the side view, you'll get cracked sidewalks that look like this. And there's a bunch of these here in Powell. If any of you have ever, if you're ever a pedestrian in the city of Powell, there's a bunch of sidewalks that have cracked due to temperature expansion. There are a lot of other examples, but this is just one that comes to mind. Now, has anyone in here taken surveying from me? I don't think so. Okay. When you measure things with a steel tape, which just looks like a tape measure, if you're measuring long distances, you also have to take into account the expansion of the tape measure due to hot temperatures and the expansion of, or the contraction due to cold temperatures. So in general, things like this that are measured, that are used to measure, are standardized at a certain temperature, meaning that at, say, 70 degrees Fahrenheit, you can, that's where the length is measured. So if the temperature is higher than that standardized temperature, which we often call T sub 0, whatever that number is, then it will expand and it will contract otherwise. Yes, Christian?
Even on small parts and quality control, they have nowadays sensors on the parts.
Yes.
That equals the temperature expansion.
Exactly. That's a very, very good point. And it's very true, especially when you have machine parts and the tolerances are quite small. That becomes an extremely important factor to the functioning of the equipment. So how does temperature expansion work? Well, it amounts to this idea is that alpha, which is a Greek letter, stands for a quantity called the coefficient of thermal expansion, which is specific to every type of material. Some materials expand quite a bit due to temperature change, some less. Yeah?
What is that? I don't know what that symbol's called, but after your rectangle, you drew a
Del, right.
The del, and then after that, what is that?
This is just like a little, a size symbol.
Okay.
Yeah, just saying that it expands some amount. And of course, that's greatly exaggerated. On problem 241, for example, when I worked it out, if you look at the value of del, it's actually measured in micrometers, which is 10 to the negative 6. So it's it's some number of thousandths of millimeters, 46 micrometers. So in other words, expansion and contraction tend to be extremely small numbers because most materials do not expand or contract a great deal based on how much they're pulled. Now some do. For example, if you think about silly putty, if you have silly putty and you pull on it, it's really easy to pull on. It expands quite a bit. Also doesn't hold stress very well, right? So don't want to build your house out of silly putty. Bad idea. So anyway, the coefficient of thermal expansion is specific to each material, which when I say it's specific to different materials, what that means is it's probably tabulated somewhere, and it is in fact tabulated in the back of your book in the appendices, similar to the values of modulus of elasticity that I showed you last time. So the equation basically looks like this, that del, the change in length due to temperature, del sub t, is equal to alpha, which is that coefficient of thermal expansion, times delta t, the change in temperature, either from between two temperatures or between a temperature and a standardizing temperature, times the original length. Now, if you run the numbers on this, del is going to be in dimensions of length, as is L. So delta T is going to be in units of temperature change, degrees, either centigrade or Fahrenheit. And so alpha is going to have the dimensions of per degree. So in other words, a degree to the -1. Okay? Either degrees centigrade to the -1 or degrees Fahrenheit to the -1. Now, since we're talking about a delta, it doesn't matter if you're talking about absolute or ordinals. So in other words, you can talk about degrees centigrade, degrees Kelvin, degrees Fahrenheit, degrees Rankine, because the delta is the same. Okay, in other words, if you're subtracting Fahrenheit from Fahrenheit, it's the same as subtracting Rankine from Rankine because you're subtracting off the base. Anytime you use a temperature, not a delta, not a change in temperature, but a temperature, you need to make sure that you're using either absolute or non-absolute, something with a non-meaningful zero in the equation, depending on how the equation is written. Yes?
What degree is that?
Sorry?
It says something degree.
Here?
Yeah.
Centigrade? Per degree.
Per degree.
Yep, per degree. Okay. So what this means to us is, first of all, since we know that del due to T is equal to alpha delta TL, we also know that epsilon, which is equal to del over L in general, is going to just equal alpha delta T, and that will be dimensionless, right? This will be in dimensions of length. This will be dimensionless. Now, the other thing is, therefore, for del due to temperature, del is not a function of stress, right? In other words, if it is not restrained in any way, the expansion or contraction will occur without having any stress. However, if the expansion or contraction is restrained, stress will be induced. And that's what happens when we see the sidewalk crack. The del, if you just had a block of concrete sitting out in the middle of nothing, as it expands or contracts, it wouldn't buckle. There's no strain or stress being put on it. The strain or the del is occurring without a stress. However, when you restrain it, it then results in having a stress associated with a restrained expansion. All right, so I want to take a look at a couple of problems, and I'm going to ask you a couple of questions. So I'm going to start, I think, let's see. I want to find a good problem with a good delta T in it. All right, let me look at aluminum, 57. Let's look at 58, 2.58, where we can apply these ideas. 258, we have a composite rod that is welded to a wall on the right. We have a larger portion made of aluminum and a smaller portion made of brass. And we have a 0.2 or 0.02 inch gap between the end of the brass and the wall. Now, it tells us that this gap exists at a temperature of 75 degrees Fahrenheit. So that means that that's really our standardizing temperature. We've measured this gap when the temperature is 75 degrees Fahrenheit. But it says then, determine the temperature at which the normal stress in the aluminum bar is equal to 11 KSI at T equals question mark. Okay, so there's a lot of questions that we need to answer, and then the corresponding length, so in other words, L plus del of the aluminum bar. All right, so what are we really talking about here? What we're talking about is if we increase the temperature to a certain point, that 0.02 inch gap is going to be filled, isn't it? So in other words, the brass and aluminum together will get longer and they will touch the wall at some point. What happens after the brass portion of the rod touches the wall? At that point, the wall is going to start pushing back, isn't it? So there are really two parts to the problem. There's one part where we fill that 0.02 inch gap at which there is no stress. But then as the temperature continues to rise, we're going to have a stress from the wall pushing back. Okay, so let's work it out. Let's work out two ways. You can do this in one step, but I would prefer to do this in two steps. The first step is, at what temperature will the gap close? So when it just touches the wall. Well, the answer is that del due to temp is equal to alpha delta T times L, but we have two parts, right? We have alpha delta TL in the brass and the aluminum. And the del T that we're interested in here is 0.02 inches. All right, so we are given some information about the bronze rod and about the aluminum rod. We're given the cross-sectional area, so we don't have to compute that. The area here is 2.4 square inches. And the modulus of elasticity, E of the brass, is 15 times 10 to the 6th psi. And the the coefficient of thermal expansion is 12 times 10 to the minus 6 per degree Fahrenheit. You notice that's a very, very small number. Coefficients of thermal expansion tend to be very, very small numbers. For the aluminum, we're told that the cross-sectional area is 2.8 square inches, that the modulus of elasticity is 10.6 times 10 to the 6th psi, and that the coefficient of thermal expansion is 12.9 times 10 to the negative 6 per degree Fahrenheit. All right, so this is a lot of data, but for the, yes? It was okay.
I was just wondering, when, maybe it's just all metals are the same, but when you have a material that keeps expanding as energy's being added to it, does it actually go like consistently before it hits its melting temperature? No. That's an excellent question. When you start to have phase changes or molecular structural changes, everything changes. So this is really when you're just in the thick of that solid state. And some metals have more than one solid state, so it's all over the place. Yeah, so we've really defined this problem very narrowly. We're not melting the brass, or the bronze, or the aluminum. I was just wondering,
Yeah.
Would it continuously expand before it just started to drip, or would everything?
No. Things change. They're very, very different. An example of that exhibits a strange change is water right around the freezing temperature. Because as you know, water, if you look at frozen water, which is solid water, it floats on top of liquid water, which is quite unusual. It's a different property. But if you look at the expansion and contraction due to temperature changes right around zero, it changes in a very strange way. So this is really assuming that we are in a range where this linearity occurs, and we haven't really discussed what would boost us out of that linear range. So, yeah. But it's a good question. But so we're not going to melt the brass or the aluminum. We're not going to bend it. It's just going to take the stress that we're going to give it. Okay? So in the first part, there's no stress at all, right? When we're expanding up until the time that it touches, in other words, when the del is 0.02 inches, we have zero stress. But 0.02 then is equal to alpha, 12 times 10 to the minus 6 per degree Fahrenheit, times delta T, which is our new temperature, our higher temperature. That's the temperature where it touches, minus 75 degrees Fahrenheit. So this and this cancel out, times the length of the brass, which the problem tells us is 14 inches. And we add to that the alpha, which is 12.9 times 10 to the minus 6. Now the temperature, the high temperature is going to be the same. That's actually the variable that I'm going to be solving for. Minus 75 times the length of the aluminum rod, which is 18 inches. Okay, so the first thing is, in this first part of the expansion then, if I'm going to be solving for T sub h, we get 0.02 equals, I'm going to distribute, the first thing I'm going to do is multiply this by this, same over here, so I'm going to multiply 14 times 12 times 10 to the negative 6, which is 168 times 10 to the minus 6 times T sub h minus 75, plus, then I'm going to take 12.9, multiply it by its length, which is 18, 232.2 times 10 to the minus 6, also times T sub h minus 75. Okay, so now I'm going to distribute this through. 0.02 then is equal to 168 times 10 to the minus 6 times T sub h, minus that number, 168 times 10 to the 6 times 75, which is 12,600 times 10 to the negative 6. And I'll distribute this through 232.2 times 10 to the negative 6 T sub h minus 75 times that number. Which is 17415 times 10 to the minus 6. All right, now to do my arithmetic, I need to pull the two constants together, 12,600, which is negative, and 17,415, which is negative, so I add the absolute values. And that value is negative 30015 times 10 to the negative 6. Then I add these two values, and that's my coefficient of T sub h. So I have 168 plus 232.2 times 10 to the minus 6. So this plus this is 400.2 times 10 to the negative 6 T sub h equals 0.02. All right, so this comes over to this side as a positive. And if I wanted to write that as 10 to the minus 6, I don't know if I want to do that or not. I'll just do it this way. If I take this number, 30015 times 10 to the minus 6, and then it becomes a positive on this side of the equation, plus 0.02, that number together is 6.03. Yeah, that's right. 0.05. I'm going to carry out some decimal places for a minute. 0015 equal to 400.2 times 10 to the negative 6 times T sub h. Okay. So then I divide by the coefficient on T sub h. T sub h is equal to this number divided by this number. And that would be 10 to the minus 6 in the bottom, so 10 to the positive 6 in the numerator, so I multiply by 1,000, or a million, excuse me. I get T sub h is 124.97 based on my work. That's in degrees Fahrenheit. So I'm going to call that 125 degrees Fahrenheit equals T sub h. Okay, so what that tells me is when the temperature rises from 75 degrees Fahrenheit to 125 degrees Fahrenheit, this gap is going to be closed. Okay? And there's no stress at this point. But as the temperature increases to some new T sub h, stress is going to occur. So now we have this situation. The temperature is 125 degrees Fahrenheit. And now I'm asking, what is the temperature? I'm going to call it T sub HH for the second high, or high squared, right? Because I got it one. This is sort of like my intermediate high temperature. I want to know what the temperature is going to be when sigma is 11 KSI, which is 11 times 10 to the third PSI. All right. Well, what's going to happen? Once it touches and it continues to expand, we're going to have a force pushing back, a reaction at this wall, which is going to be equal to the reaction at this wall. Right? And it puts the whole thing into compression. So how does that occur? Well, the first thing we can say is that the new del, the del after it touches, is going to equal 0. And there are 4 things that are going to be happening. We're going to have an alpha delta TL that is expanding the brass rod, and we're going to have an alpha delta TL that's expanding the aluminum rod, and then we're going to be pushing back, so it's negative PL over AE of the brass rod minus the PL over AE of the aluminum rod. Okay? And those things added together equal 0. I do not know what this is. I don't necessarily know what this is, except to say that it's equal to the same as this, right? The force in those two things is going to be the same. Okay? And I also know I can find that because I'm told that if at sigma in the rod, in the aluminum, is 11 times 10 to the third psi, we also know that that's going to equal the force divided by the cross-sectional area. So we can use that to solve for P, because I know what A is. Right? So I'm going to do that to solve for P, and then I can put that back into this equation to solve for T. All right? So since sigma in the aluminum is equal to 11 times 10 to the third psi, which is equal to this unknown force P over the cross-sectional area of the aluminum, which we're told is 2.8 square inches. I then can use this equation to say 2.8 square inches times 11 times 10 to the third psi, which is pounds per inch squared, is equal to P. And I can then solve for P, 2.8 times 11, which is 30.8 inches times 10 to the third pounds. All right? And I have 6 minutes left. I wonder if I can get finished. I think I can. Okay. So we take a look at this then. And I'm going to do something a little bit different. I'm just going to leave this value as delta t instead of putting in the negative. Now 125 would be on the bottom, because in other words, we're looking at how much it increases from 125. But if I leave it as delta t, I can just solve for delta t without doing all that distribution. And then I can just add it. I can just do my delta t equals high temperature minus 125. So that's just a little arithmetic simplification. All right, so I get 0 is equal to alpha delta t L in the brass, which is 12 times 10 to the minus 6 delta t times the length of the brass, which is 14 inches, plus alpha 12.9 times 10 to the minus 6 delta t times that length, which is 18 inches, minus P 30.8 times 10 to the positive third times L, which is 14, over A, which is given as 2.4 inches squared times E, which is 15 times 10 to the 6th, minus, now P over A here, I could put in the 30.8, or I could also just recognize that P over A is the 11 times 10 to the 3rd PSI. So that's P over A, right? So this is P times L, which is 18, over A, which is already figured into here, times E, which is 10.6 times 10 to the 6th. And those things added together equal 0. All right, now these two terms are constants, and these two terms are both multiplied by delta t. So I'm going to say 0 is equal to this times this. I'm going really fast because I only have a few minutes. 12 times 10 to the negative 6 times 14. And then I want to add to that this. Do I have a plus yet? There we go. Plus 12.9 times 18, parentheses, equals. So this and this is 400.2 times 10 to the minus 6 delta t, minus, and if I do this quantity, 30.8 times 14 divided by 2.4 and divided again by 15 times 10 to the 6th. This quantity is 11.98 times 10 to the negative 3rd, because I have a 3 and a 3, so this cancels that, it's negative 3. Minus this, 11 times 10 to the 3rd, times 18, divided by 10.6 times 10 to the 6th, is 18.68 times 10 to the minus 3rd. Okay, so I bring these two terms together. They're both negatives over here. So I add their absolute values, and I get negative 30. Comes over here as a positive 30.66 times 10 to the minus 3 equals 400.2 times 10 to the negative 6 delta t. So to solve for delta t, I take this number and divide it by that number. So I have 30 divided by 400.2, and that number times 10 to the 3rd, 1, 2, 3. So I get 76.6 degrees Fahrenheit is delta T. All right, well that means that my temperature, my high temperature, because this is my delta, right, so this is T sub H minus that intermediate temperature of 125. So that my T sub H is 76.6 plus 125, which is 201.6 degrees Fahrenheit equals T sub H. So the answer to the first part of the question is the stress in the aluminum rod will reach 11 KSI when the temperature is 201.6 degrees Fahrenheit. Now, the next question is, how long does the rod become? And what you need to do at this point, the del of the aluminum is equal to the del due to temperature in the aluminum plus del due to the stress, sigma. This is going to be positive, and it's going to be alpha delta T. Now, this is from the low temperature because it expanded to the very highest of temperatures. So it's 201.6 minus the original temperature of 75 times the original length, which is 18 inches. Then the stress from the pushback is negative, so it's PL over AE, or sigma, because that's P over A, times L, which is 18, over E for the aluminum, which is 10.6 times 10 to the 6th. Okay, and if you look at that, these are in inches, so that's going to be a del in the aluminum in inches. And if it's positive, that means it expanded, and if it's negative, then it means it contracted. So what's my alpha for the aluminum? 12.9 times 10 to the negative 6. Okay, so let's find what it is. 12.9 times 10 to the minus 6 times the quantity 201.6 minus 75 times 18 inches. So this quantity is, I gotta divide that by a million because it's 10 to the minus 6. 1, 2, 3, 4, 5, 6. So this is 0.0294 inches minus 11 times 18 divided by 10.6. And then this is divided by 1,000. So it pushes back 0.0187 inches. Okay, so what that means is it expands more than it contracts. So my del in the aluminum is a positive 0.01 inches. So 0.011. But that means that basically the aluminum moved this way. This end of the aluminum moved 0.01 inches, or 1/100th of an inch to the left. All right, do you guys have any questions? I ran out of time. All right, so I'm going to quit streaming.